morning. Okay, so this is the last live session of the term, and I am covering exponential models of growth and decay. So models are equations we write to represent word problems specifically. And so we're going to be covering word problems involving exponential growth and decay, obviously from the title. So when we've got exponential growth and decay, we have a specific equation for that. Now, there are different ways to write exponential equations. There's different forms, so I will go into the difference between the different forms. But if you hear the words exponential growth or exponential decay, we generally assume it's going to be this particular model where you have E in your model, Y equals Y naught E to the KT. So K is generally some percent of growth. A T usually represents time. Y0 or Y naught is your initial value, basically what you're starting with. And then E is Euler's number, which is the special number on your calculator, 2.7182, I think is all the decimals I know. It actually rounds to 2.7183. I round that correctly, but it's a special constant that we use. So when you see exponential growth or decay, this is generally what we're talking about. And it's growth if K is positive, and so it's going up. And then it's decay if K is negative, so it's going down. So like I said, there's different model types. And so a very similar looking model is on the left, Y equals Y naught B to the X. So these are both used with word problems, and they both are used when things are kind of growing or getting smaller. The key is the wording. So if you see something like per or each in your word or in your word problem, like something is growing per year, per day, each year, things like that, then you're going to be using the model on the left. And we can replace B with 1 plus or minus R, plus if you're growing, minus if you're decaying or getting smaller, and R is your growth rate, your percentage rate. You use the model on the right if you don't see the word per or each. So this will have the word continuous in it, or it may not mention anything at all. It won't say like a per year, per day, and it's something that occurs naturally. So population growth uses the model that's on the right. Anything that's like in chemistry will use the model on the right. We use the model on the left when we have things with money, because that's not really natural. The interest, the growth rate that you have when you're gaining interest on something is something that, like, you know, banks control. It's not like it's just naturally occurring. So the two models look very similar, but there are very specific situations where you use one versus the other. And so on the left, we use R to represent the rate, the growth rate, and that's usually a percentage. Your K on the right will also be a percentage, but K and R are not the same thing. And my next slide is kind of going to give you an example of this. So you can kind of see when you use each model and how they're almost the same, but not quite. So I've got 3 examples here. On the left, we have an example where we're growing per year. In the middle, we have where we're growing quarterly, which means 4 times per year. And then on the right, we are growing continuously. So it's just constant growth. So each one uses a different model. So the one on the left is our general exponential model. Y naught b to the x. The one in the middle, if you're not doing per year, if you're doing multiple times a year, then you kind of switch your model up, and you do the compound interest model. So that's what we have in the middle. And then on the right is the exponential growth model where it's like always growing. So for all three of these situations, it's 3%, but the models end up being slightly different. So I've gone through the math here to kind of, explain what's going on. So if you are growing 3% per year, 3% is 0.03. So your B is 1 plus 0.03. So that comes from this 1 plus R if you're growing. And so B, what's in the parentheses underneath your exponent, ends up being 1.03. So that's when you are growing each year. If you're growing more times a year, you need to switch to the compound interest formula, essentially. And so if you're growing quarterly, that's 4 times a year. So what happens is you end up dividing by 4, but then you also have to multiply by 4 up here in the exponent. So when you go through the math, you still have that 3%, but you're dividing it by 4. So that gives you this number. Then you add those together, but you have this exponent of 4t instead of just regular t. So our rules of exponents say that we can take that 1.0075 and raise it to the 4th power and then have it to the exponent t. And so that's what we do here. And then that gives us this final number. So these are both growing at 3%, but the actual values for B are different. So B is 1.03 here because that's per year. If you're doing it 4 times your year, your B is 1.03. So it looks the same, but there's actually more decimal places. So it looks almost the same, but not quite. It's the same up to a certain point where you're rounding, but there's actually more going on there. And then when we are growing continuously, we use the model with E, and your 3% is then used for K, and use a positive value for growth or negative for decay. So we're going to have a 0.03 up there. And then we're using the same rule of exponent that allows us to do E to the 0.03 and then put the T on the outside of the exponent. And that gives you this 1.0304554534. And so B here is 1.0304554534, and it keeps going. So all of these values for B, when you put it in the same form, round to the same thing, 1.03, which would be 3% growth. They all are basically 3%, but we're using different models and they're only the same when you round to a certain point. There's actually more decimal places the more times that you are doing the interest essentially on this. And so the numbers are not exactly the same. And that's why it's important to know which model you're supposed to use. Because if you round them to a certain point, they're exactly the same and it doesn't matter. But it will matter when you start using the formula, because then your numbers will start to be different. And so, and that could cause a problem when you're in ALEKS. If you use the wrong model, you might start getting your answers wrong because of the rounding issue, because while these round very close, they're not exactly the same. So we're going to do some examples where I'm going to kind of show you how you know which model you use when you are trying to write the formula. And so we're going to basically use these three forms, whether it's something per year, something more times a year, and then continuous growth. So we're just writing the models here. So our first one, a couple has $25,000 in a retirement account that grows by 3% compounded continuously. So you're looking for key words here. And the word continuously, that word tells us we're using the model y equals y naught e to the k t. So if you see the word continuously anywhere with compounding, that's the model you're using. So like that would be the first thing that I look for, is to see, do I have that word? Because then I know exactly which model I have to use. If you don't have that word, then you have to decide between the other two models, determining basically by how many times a year it's occurring. So our second example here says $20,000 is invested at 2.25% interest compounded semi-annually. So it doesn't say continuous. So we're either going to be using y equals y naught b to the x, or put it in the form of like a equals p 1 plus or minus r over n to the nt, the compound interest formula. If it's yearly, you use the one on the left. For everything else, you're going to use the one in the middle. So it says semi-annually, and that actually means twice a year. So that is a word that means twice a year. So if it's happening twice a year, that's not yearly because it's happening more often. And so you use your compound interest formula. And these are all growth. So they're all going to be positive here. So that's the form that the model takes. But when it says find the model, it doesn't just want, well, which of these equations do you use? We want you to actually plug in the numbers in the right spot. So for the first one, we've got $25,000, which is the starting point. So y naught is your starting point. So y naught is 25 grand. And then you have E, and then K is your percent. So it's 3%, and if it's growing, it's positive. So it's going to be 3%, but we need to convert that to a decimal. So you do that by dividing by 100. So 0.03 and then T. So once you've determined which of the three forms it takes, then you just need to figure out what is your starting value and then what is the percent. And you can just plug that in. And then that is your model for the situation. So for the second example here, we're starting with $20,000. So in the compound interest formula, that's your P. That's what you're starting with. So notice what you're starting with is always in front. And then the 2.25, that is R. And so you need to convert that to a decimal. So you divide it by 100. So you get 0.0225. And then semi-annually twice a year means that N is equal to 2. So our 20,000, that is P. So you have to figure out, okay, what number, what words, are indicating what parts of this formula, and then you can plug it in. So we've got A equals 20,000 times 1 plus 0.0225 over 2, and then 2 times the 2t up there. It's twice a year. Now, generally what we will do is simplify in the parentheses. So we will do that division, divide by 2. And then we will add 1 to that. So we usually simplify this to say A equals 20,000, parenthesis 1.01125 to the 2t. So that is the model that you would use then if you were in that type of situation. So if there are questions on these examples.
Can you explain the 2t again, please?
So that comes from this n times t. So n is how many times a year we're getting interest. And so because it's semi-annually, it's 2 times a year, we're basically taking the exponent twice. So that's why we multiply by 2t there. So if you wanted to know the interest after 1 year, you would have 2 times 1. You're actually having interest twice, so your exponent ends up being 2. So it's just part of the formula. Whatever your n is that you determine, whether if it's quarterly, that would be 4 times a year. Monthly would be 12 times a year. You just plug that in for n into that formula. Does that help?
Yes, thank you.
Okay. There are other questions? Okay. So here's a couple more. These are much more wordy. Directions are slightly different. It just says write an exponential function showing the relationship between y and t. So it's telling us specifically the variables that we're going to be using are y and t. So we may have to, if I go back, this middle formula, if you're told to use y and t, you already have t in there. You just have to switch your a to y. And then you're basically using the same thing. So that would be like y equals y naught 1 plus or minus r over n times nt. So it's just a slight change from a and p to y and y naught. So if you're just told to use different variables, there is just different names for them. So first one, we have at the beginning of an environmental study, a forest covered an area of 1,500 kilometers squared. Since then, this area has decreased by 9.9% each year. Let T be the number of years since the start of the study. Let Y be the area that the forest covers in kilometers squared. And we want to write our function. Again, this is word function, just means equation. It just means we're writing our model. So I read through and I ask myself, do I see the word continuous? And the word continuous is not anywhere in that little paragraph. So then I look to see if it's like an each or a per or things like that. And we have each year. So when you see each year, that tells you that you're using the model with b to the x. But in this case, because we're using t as our input, it's going to be b to the t instead of x. But each year, so if it's something happening once a year, that's the model that you're going to go for. So I look there. And so now I need to kind of figure out what my numbers are. So y naught is your starting amount. So it says at the beginning of the environmental study, a forest covered an area of 1,500 kilometers squared. So it said at the beginning, so this is our y naught, is the 1,500. Now, our B here is not a percent. We're being given a percent. It's being decreased by 9.9% each year. So this is where we go back to the fact that B is equal to 1 plus or minus R. So it'd be 1 plus a percent if we're growing, or 1 minus a percent if we are decaying. So we are given a percent, it's decreasing, so it's going to be 1 minus R for RB, because if you're decreasing, it's going to get smaller. So that's where we get the word decreased. And then that 9.9%, that isn't our value for R, but we need to divide it by 100 because we need to convert it to a decimal. So that would be 0.099. So once you figure that out, you start plugging in your numbers. So Y naught is 1500. B is equal to 1 minus R. And then we have R. So I can replace R. It's 1 minus 0.099. And now we usually simplify and do that subtraction, that 1 minus 0.099. And so that will give us our model Y equals 1500. And then in parentheses, 0.901 to the T. So to recap here, first thing, I looked to see if it had the word continuous anywhere, and then I looked to see if it told me how many times we're decreasing or increasing. And it said each year, so that each year tells me that it's not continuous. And because it's happening yearly, that told me it's Y equals Y naught B to the X, or B to the T. And once I've determined that model, then I have to figure out the numbers, where they go. Your starting amount, your percent, and then you have to determine B is either 1 plus a percent or 1 minus a percent. And in this case, it's decreasing, and so it's minus. So the second example on here, we've got an initial census taken in a small Asian country found the population to be 22.9 million. The population growth rate is 0.34%. Let Y be the population in millions. And when they say parentheses in millions, that means you don't need to convert the number to actual millions with all the zeros. You can just use the 22.9. And T be the years after the initial census for the Asian country. So I look, do I have continuous written anywhere in there? So the word continuous is not in the problem. So next, I'm looking to see if I'm like doing something per or each. It doesn't tell us that either. It doesn't say that the growth rate is each year. It doesn't say that that is like each month or each decade. It doesn't tell us how often that population growth rate is happening. So if I go back to, this one here. So there was nothing to indicate continuous. We don't have anything specifying yearly, and we don't have anything telling us how many years it is. So it's kind of like, okay, which one of these is it? So when you can't clearly indicate which bucket it goes into, then we go back to, is this something that's growing naturally? And population is something that we consider growing naturally. And so we always assume the continuous version if it's not specified. So we are assuming that this is continuous growth. And we're going to use the e to the kt version of the formula. So basically, you try to see if you can assign it immediately with the word continuous. If not, you try to rule out the per or the each. And it's like, well, if it's not the per, the each, the other model, then it has to be this model. So with population, we generally always use the e to the kt unless it has per year or something like that in there. So we're going to be using y equals y naught e to the kt. So y naught is the starting amount. So that 22.9, that is y naught. And we don't need the million. We just are caring about the number. And then the growth rate here that they're giving us, that is k. And we always convert it to a decimal. So I have to divide that by 100. So it's going to be 0.0034. So it's already small at 0.34%. It's going to be even smaller when we convert that to a decimal. So then that gives us our model, y equals 22.9 e. And then when you're growing, it's a positive value for k. So it's going to be 0.0034 t. So we had to kind of rule out that it wasn't like growing per year or anything like that. And then from there, you can use the E model. So are there any questions? Okay. So now we're going to actually kind of do more than just write the model here. We're actually going to be solving some problems. So an initial census taken in a Scandinavian country found the population to be 7.3 million. 10 years later, the population had increased to 7.8 million. Write a function to model the population P of t in millions after the initial census, and then use it to predict the population 20 years after the initial census was taken. So we've got a lot going on here. But the first thing we need to do is actually figure out what model we're using. So you read through it and you say, do you see the word continuous anywhere in there? You don't. So then you want to see, are they giving you a percentage that's like each year, each month, something like that? We're not given any percentages here. Now they do tell us how much was 10 years later, but we're not getting a percent. You know, it's not saying it's growing by this percent per year. So there's nothing to indicate that we use the model with per year, that kind of thing. So then you go back to, well, this is modeling population. Population uses generally the e to the kt form. So if there's nothing that indicates one or the other, a specific type of model for population, we are assuming that we're going to use the e to the kt form. And actually, so as I have it written, we have y equals y naught e to the kt. Now they're telling us that we want to model the population P of t. So they're just telling us instead of y, put it in function notation and call it P of t, just for P for population. That's all they're saying there. So now we have to start like figuring out what numbers that we're given. So we're given the initial starting point because it says the initial census was 7.3 million. So why not is going to be 7.3. We don't need to write the million stuff. That's given to you. But they're not giving us K. We don't actually have a percent that they give us. So we have to actually find that on our own. We have to do some math to figure out what that is. And so that's where we're going to use the information that they give us about 10 years later. So 10 years later, that means that T is going to be 10. And then 7.8 million is 10 years later, so that's going to be P. So that's 7.8. And in function notation, that's actually P of 10 being 7.8 because T is equal to 10. So since they don't give us a percent, we have to actually kind of figure out what that is based off of the model. And so we plug in our numbers. So we're going to say we have 7.8 equals 7.3e to the k times 10. So you're plugging in 10 for t, and then you're plugging in 7.8 as your output. So when t is 10, the output was 7.8. So now we've got this equation that we can solve for k. Because remember, e is a special number, so we don't have two variables here. E is not a variable, it's a constant. So we need to solve this for k. And that will tell us what the actual percentage is that it's growing. So when you're solving this, you need to divide both sides by 7.3 because we need to get the e part by itself. So we're going to divide by 7.3 on both sides. And when you are doing this math, you want to kind of write as many decimal places as possible, because if you write too few, you're going to have issues with your rounding, and then your answers at the end are going to be wrong. So you want to kind of write down as many numbers as possible. I have found that 5 decimal places is usually pretty good. That if you use 5, you don't have to write the whole thing down, and it's enough that like when you get your final answer, like especially in Alex, you're not going to be off, you'll still be okay. So I usually just use 5 decimal places. So when I do 7.8 divided by 7.3, I have 1.068493151. So when I do 5 decimal places, that's 5 after the decimal point. So that would be after the 9, and then I have to decide how I'm rounding it. So if after that it's 5 or higher, you round up, otherwise it stays the same. So because it's a 3, I don't need to round up, so I can just use those values. So I'm going to have 1.06849. And then this is equal to e to the 10k. Instead of writing k times 10, I'm just writing it as 10k. So we are solving for k. When you're solving for your thing that's in the exponent, you're going to take a logarithm, and because the base is e, we're going to use the natural log. So I need to take the natural log of both sides. So I'm going to have the natural log of 1.06849 equals the natural log of e to the 10k. And that natural log and the e essentially cancel out. So you just have 10k on the right, and then we need to use our calculator on the left. So you have to type that in. And again, I'm going to round to 4 decimal places or 5 decimal places just to make sure that I have enough decimals. I don't start accumulating too many rounding errors, because the more you round, the more error you occur. So that gives me 0.0662464337. And so I'm rounding to 5. 1, 2, 3, 4, 5. So that is after the 4. So because the number after the 4, after the 5th place is 6, so it's higher, it's 5 or higher, I round up. So that 4 is going to become a 5 when I round. So I have 0.06625 equals 10K. And then we are going to divide both sides by 10 because we want to solve for K. And I get 0.00066625. So I went through all of this work to find out that value of K so I can actually write my model. And if you wanted to convert that to a percentage, you would multiply it by 10. So our model is P of T equals 7.3e to the 0.00066625 T. So I did the first part. It said write a function to model the population. So we've got that function. And then the second part is to use it to predict the population. So before we do the prediction part, are there any questions here? What is the symbol I used to multiply by 1.06849? Okay, that is not a multiplication. That is taking the natural log. That is an action that you are doing. You're not multiplying something by 1.06849. You're taking the natural log of 1.06849. So that's a button on your calculator. It says LN. So it actually comes from the Latin. I looked this up recently. The Latin word for natural log has the words in naturalis logarithmus. And so, or it's logarithmus naturalis or something like that. It's in the order LN. So that's why it's LN, not NL for natural log. But that is a button on your calculator. So you are hitting that button and then you're typing in 1.06849. And that's taking the natural log. It's like you take a square root. It's just an action you are doing to a number. Are there other questions? Okay, so second part of the problem is to predict the population in 20 years. So that is just telling us that T is equal to 20. So now that I have my formula, I just need to plug in 20 for T and then follow the order of operations. So you need to make sure that you're writing all of your numbers correctly. So order of operations says we have to do the exponent first. So in the exponent, I need to multiply the 0.00066625 by 20 first. So I have to do that multiplication in the exponent before I do anything else. And so that gives me 0.01325. Order of operations, we're still in the exponent step. I need to take the exponent. I need to do e to that exponent. So I'm going to raise e to that exponent of 0.01325. And that gives me 1.013333817. And then I want to multiply that by 7.3. So the last step is to do multiplication. And that gives you 7.397368641. Now we are predicting a population. So this is in millions because the population numbers were all in millions. And this number, I must have made a math error somewhere because this number is smaller than the 10 years later population. So either I typed in a number wrong or something else. So you want to think about this population is supposed to be growing. So I just got a number smaller than the 10 years later. So at 20 years later, it should be even bigger. So does anybody know where I might have made a math error? Ah, I found it. I had too many zeros on my K. So it should be 2 zeros. I put 3 zeros. So that's going to change these numbers. So be very careful that you count your zeros correctly. And also double check that your numbers make sense. Okay, so correcting that, this becomes 0.1325. This becomes 1.141679016. Okay, much better. Now I get 8.3342568117. So I should get a number bigger because we're growing. So 20 years later should be bigger than 10 years later. So it's always good to kind of check yourself and whether the number makes sense. And because I discovered, oh, that doesn't make any sense. I had to go back and find my math error. And it was just, I had too many zeros. So you want to be very careful. It's very easy to make an error like that when you've got small numbers like this. So generally when we're giving our final answer here, so first off, the question was, find the model. So that's our model. And if we want to predict the population in 20 years, because the other population numbers are given with 1 decimal place, then we also want to use 1 decimal place when we're predicting our population. So 20 years later, the predicted population would be 8.3 million. Are there any questions?
Can I ask you a question? So on the blue side where this says P20 equals 7.3 E,
Yeah,
how did you just multiply or did you divide the 20 to the other side, or how did you get rid of the 20 on the P side?
the 20 is not gotten rid of at all because in
Okay.
function, when you have function notation,
Oh, I
the
see it.
P of
Okay.
20 just stays there. So that's why I didn't even touch it and I just left it because we're not solving anything. We are evaluating a function for T being 20. So function notation, you never divide by that number on the left side. So
Okay, you just plugged it in.
I just plugged it in. So yeah, so I just leave it there because if I keep writing it, it's too tempting for people to divide by 20. So I just don't do it and I'm only working on the right side.
Got it. Thank you.
Yep. Other questions? Okay, so I've got one more example. The isotope of plutonium-238 is used to make thermoelectric power sources for spacecraft. Suppose that a space probe was launched in 2012 with, whoa, I really had a major typo there. I think I was trying to backspace and apparently did it. 2 kilograms of plutonium-238. If the half-life of plutonium-238 is 87.7 years, write a function of the form Q of T equals, gosh, that's supposed to be an underscore. I really was not noticing my typos here. Q naught e to the negative KT to model the quantity Q of T of plutonium-238 left after T years. So the nice thing here is they're telling us what model to use. It's essentially the same model we just did with continuous, but we're using Q because Q is usually used for decay. So, and for the word quantity, so it's just switching letters there. And then notice that we have a negative in front of K, and that's because when you're decaying, you're getting smaller and it's decreasing. So that negative is indicating that we're decreasing. So we are using the model Q of T equals Q naught E to the negative KT. So all we're doing here is just to write a function in that form. So we need to find out what Q naught is, and we need to find out what K is. So K is always a percent, and they don't give us a percent. So we're going to have to solve for K just like we did with the other example. But they did give us Q naught. Q naught is your starting amount. So we are starting with 2 kilograms. So that is Q naught. So I can plug that in. That's going to be just 2.0. We have 2 kilograms of the plutonium. Now, the other information that they give us is that the half-life is 87.7 years. So that's giving us a value for T to plug in. But we need to know, well, what is the quantity after that time? Half-life means you have half of what you started with. So half-life means you have 1/2 of your starting amount, Q naught. So that means we have 1/2 of 2 kilograms, or we basically have 1 kilogram. So this gives us a value to plug in for Q. So we have 1 kilogram after 87.7 years. So that half-life is just saying half of whatever you started with. So this allows me to plug in numbers here so that we can solve for K. And so I plug in 1 for my Q, because that's, after whatever, and I don't have to use 2.0. I can just use 2 instead of not having to have that 0.0. equals 2 times e to the negative k, and then we're plugging in for t 87.7 because that's after how many years we get half of the amount. And so now we want to solve for k. So we're going to divide both sides by 2, just like we did in the other example, which gives us, you can see 1/2. So we get 0.5 equals e to the negative 87.7 k. So I'm just going to multiply that negative k times 87.7. Now we want to get k out of the exponent, so we need to take the natural log of both sides. So I'm going to have the natural log of 0.5 equals the natural log of e to the negative 87.7 k. And the natural log of e is just 1, so that cancels out. And so you get negative 87.7 k on the right. And then on the left, we need to actually figure out the natural log of 0.5. So you do that on the calculator, I get negative 0.69314.7. I'm getting all of these decimal places, so I'll just write them all out so we can round properly. 181. So just to make sure that we round enough, we'll have 4 decimal places. For 5 decimal places, I mean. So that would be after the 4 here, we have 0.69314. So there's 5 numbers after the decimal place. Because after that is a 7, we're rounding up. So if I'm going to round to 5 decimal places, that 4 is going to become a 5. And so we have negative 0.69315 equals negative 87.7 k. And now we are solving for k, so we want to divide both sides by the negative 87.7. And I kind of ran out of room here, so we got k equals, so negative 0.69315 divided by negative 87.7. That gives us k equals 0.00790364.9. I made sure I wrote down the correct number of decimal places. And so with k, we're usually rounding to 5 decimal places here, unless it's specified 3, 4, something like that. But usually 5. So I'm going to count 1, 2, 3, 4, 5. So that would be after the third 0 there. Because it's the number after my line is less than 5, I don't have to round up. So we just need to round. It's going to be 0.00790. So now we can go back and write our model. Q of t equals 2.0 e to the negative k, so negative 0.00790 t. And all it wants us is to write the model, so we don't have to do anything with this. We just had to write that model. So we had to kind of find k so that we could get that actual number there. Are there any questions? Okay. So for on the final exam, you will have one question like this where you need to find the model. So you'll have to decide which form the model needs to take. And if they give you the percent, then it's going to be like one of the first few that we did where you just have to plug the numbers in and just determine which of the correct forms it needs to take. So one of these first four. If they don't give you the percent, then you need to figure out the model and then you need to find the percent. So it would be more like something like this one with the population growth where you had to solve for K, or like this one where you have to find K and your decay. So you won't have to then use the formula after that on the final, but you will have to get the model. And so the biggest errors I see are people using the wrong model or putting the numbers in the wrong place. So hopefully this has given you enough examples that you should be able to kind of follow this from here. Any questions with that? Okay. Well, thank you guys for coming.